Hi, everybody. This is going to be cool. I got a cool question here about a rocket shooting off of the Earth and using the more accurate formula that we derived for gravitational potential energy to solve for its motion. And we're going to do it just kind of from all angles. First, we're going to really just dive into the math. So here's the situation, and it's always helpful to draw a picture, right? But I'll write the information. The initial velocity of this rocket is straight upward at 20 kilometers per second. So instantly, we're going to want to convert that to meters per second if we plug that into an equation. Please do that instantly on your own. That's what I'm doing right now, but I won't necessarily do it for you. But I'm just showing you that's what you should do first. Do that first. Obviously, we need the mass of the Earth, 5.9722, but I'll round to 5.97 times 10 to the 24 kilograms. And of course, the radius of the Earth, which is the initial radius of the rocket, initial radial distance of the rocket is the radius of the Earth, which is 6.378 times 10 to the 6 meters, or 6,378 kilometers. But I'll start in meters, make that easy. So that's our information. Obviously, we know big G, but I'm not going to write it. So here's a picture. We're going to fill this picture in um, as we go along, probably on the next slides. But just to draw an initial picture, we have like some rocket here, right? We have some rocket and it has some initial velocity. And of course, gravity is going to slow it down on its way up, taking away energy, right? So the work from gravity will be negative because the force is taking away energy from our velocity. You can see it's just, or you can call it a negative force. Negative just means it's against the direction of motion. Cool. So what are we doing? We have some initial kinetic energy, we have some initial potential energy, and we'll have some final kinetic energy and some final potential energy. And the question's going to be what happens? That's like the general question, but that's a very full question. What happens to kinetic energy? What is kinetic energy final? What is potential energy final? What is the total energy? What happens to F, velocity, etc., conceptually? Um, how far does the rocket go? Is there a final radius, or what is the final distance it goes? Right? Which might be infinite, might go on forever, or it might stop and turn around. How do we figure this out? Well, here's how. So here's the information, here's the setup, here's a little background. Let's start the analysis. So we've written down our information, we've drawn our picture. This is always step one, is to do this. Ground yourself. Ground yourself with the information, ground yourself with the picture. Don't just start plugging stuff in. Never do that. Never start plugging stuff in. Always get a lay of the land first. I cannot emphasize this enough. Set up your information, set up your picture, write down the question. What am I looking for? Great. Now we can write down equations and start plugging stuff in. So let's do that. So the equation we're going to want to use is, of course, conservation of energy. Since I want to know what happens to the velocity and to the distance, well, that's contained in the energy. I also want to know what happens to the energy. That was part of the question of what happens. Well, what's happening to the energies? And we know that the potential energy formula is negative Gmm over R. And of course, kinetic energy anywhere is 1/2 mv squared in general. So you can do this one of two ways. I want to emphasize this. You can do this one of two ways. Let me write down both ways. The first way is where you literally plug these equations into here and you write negative. Don't forget the negative. I'm pausing. Don't forget the negative. G, M, M. I wonder how many people are going to forget that negative. Don't. Let's be zero. Zero people forget the negative, right? Don't be the one. Don't be the one, right? So negative, remember, potential energy is binding energy. This is a form of binding. Binding meaning gravity binds things together. And remember, any attractive force always has negative potential energy. So conceptually, this is always negative, right? We're in a potential energy well. If I graph potential energy versus distance in general, it's going to be a well that looks like this. It's like you can think of the Earth creating this potential energy well, and the potential energy asymptotically approaches zero as you get to infinity, right? And so it takes energy to come out of the well. It takes some energy, kinetic energy to come out of the well. You might make it, but you might only make it halfway, quarter of the way, and then you come back. An object that goes up must come down unless it goes fast enough, and then it escapes, right? So that is potential energy plus initial kinetic energy equals negative GMM over R final plus 1/2 MV final squared. You can do it that way. Another way that you can do it is you can solve for these values separately. If this equation just feels too cluttered to you, method two is you solve for the initial potential energy first. This is actually what I like to do. I actually like to do method two. And I'll tell you why. So that's what I'm going to do right now. So I'm actually going to asterisk and kind of highly recommend method two. This is more dangerous and you miss information here. You miss a chance for information. If you do this, this is less successful and more ripe for calculation error, but it works. I won't stop you. If your brain likes this tons more, go for it. You can still answer all the questions, but I'm going to recommend this and I'm going to show you why. So if you plug in all the numbers here, you get negative G M M over R. Oh, sorry, there was a mass of the rocket I was supposed to say. I kind of just made this up. A tiny rocket. Remember, it's irrelevant for solving for the final velocity and whatnot, but I want to actually get a number here. I want to get an actual number. So I want to get a number of joules. So let's say a 2,000 kilogram rocket. That's like a small sedan size little mini rocket going into space. Let's just do that. So I plug in G, I plug in M, I plug in M, and I plug in R naught. And I'll just tell you what you get is negative 1.25 times 10 to the 11 joules. So this is 5.97 times 10 to the 24. This is 2,000. This is G, 6.67 times 10 to the negative 11. This is R naught, 6.378 million. Great. Plug that all in. Don't square it. This is not force. This is energy, and energy is an inverse law, not an inverse square law, due to the work energy, how we calculated it, right? You get that many. Cool. Negative. Great. That's the well. That's how much energy you need to escape. That's a great way of looking at the negative binding energy. We need at least this amount to escape. Conceptually, do you see why we're missing information if we do it this way? If we're doing it this way, we're not looking at it one at a time necessarily. You're just plugging it all into a calculator. Here, I'm looking at it as conceptually, we need this amount to escape. That's why this is so useful to organize it like this, and that's why this number is such a useful number to know. I need, what is that? An eighth of a trillion. Can you guys see that? This is 0.125 times 10 to the 12. This is an eighth of a trillion, or 125 billion joules. No big deal. I got some fire. I got some explosion. Let's do it. If my initial velocity is 2000 is 20 kilometers per second, which is, if you remember here, 20,000 meters per second, let's see how much energy we have. So I'm going to actually write it in here. 1/2 times 2,000 kilograms times 20,000 meters per second. Please don't plug in kilometers and please don't plug in grams. Please be good with the units. I know it takes some practice, but please practice that. We really need to be good with that so that that's not the mistake. Please don't let that be the mistake. Again, 0. We're aiming for 0 people forgetting the negative sign. We're aiming for 0 people forgetting how units work, because we need, obviously, without the units, we can't do anything, right? So we have, we get positive 4 times 10 to the 11 joules. I emphasize the positive because this is negative. I have positive energy to overcome the negative well. Did we do it? Yes, we did it. This is greater than that. If the initial kinetic energy is greater than the absolute value of potential energy, then negative this, then it escapes. It comes out of the well. We have enough energy to come out of this potential energy well. We have that, and we will have an excess of energy, right? So the total energy, which is the initial the initial kinetic energy plus the initial potential energy, is going to be this plus this, but that's 4 plus negative 1.25. So 4 minus 1.25 gives me positive 2.75 times 10 to the 11, 275 billion joules. Because this is 275 times 10 to the 9. If I move the decimal over right, then I move this down to 275 billion joules. But the whole point is it's positive. And if E total is positive, then kinetic energy is enough to escape, and it escapes. If E total is negative, that means kinetic energy was not enough to escape, and it falls back. Gravity wins. The binding energy says you will not go away. It is binding. But if kinetic energy can overcome the binding energy, then it has enough excess energy to go away forever. So an object that goes up doesn't always come back down. It's going away if this is bigger, and it comes back if potential energy in magnitude is bigger. So if E total is negative, then it falls back, right? And that's the concept we want to know that connects to these numbers, which is why, do you see the asterisk? That's why I really recommend this, this way of looking at it. I highly recommend this way of looking at it over here. If you just do this, you will get an answer, right? But it won't have as much conceptual depth. You're going to be missing information. So I'm going to kind of insist you do that. And a lot of my questions will ask for these things explicitly, but if they don't, just showing you this method. So cool. Pause the video if you need to go through it again, but I'm going to move on to like more analysis of this. So we have the total energy, but remember the question was, well, what happens? Well, it escapes. But what are the final kinetic and potential energy? We've solved for the E total. Great, we've solved for that. We're going to talk about this. We want to talk about what happens to these conceptually. And ultimately, what is our final? Well, let's do this a little more cleverly. A little, instead of just saying RF is infinity, let's take our time with this. So let's assume, switch colors here. Let's assume that it does come to a stop. Then if I set up this equation, I'm going to switch back. If I set up the equation that energy is constant, remember this is E total. And this is also really important to know that this equation means E total equals E total. This is like 10 equals 10, or in this case, 2.75, sorry, 275 billion, 2.75 times 10 to the negative 11 equals 2.75 times 10 to the negative 11. But the forms have changed. What form does this amount of joules take now? This used to be negative 1.75, or sorry, 1.25 times 10 to the 11 and positive 4 times 10 to the 11, right? But now what is it? So if we assume V final to be 0, which means we assume it falls back. Say we just assumed it fell back. Say you did this method here. Say you did this method here and you said, I'm going to assume V final is 0. Well, what is V final? What is R final? How do you know what to plug in? So doing it this way is dangerous. You miss information. You're not sure what happens. Here, I know it escapes because I know it has enough energy to escape. But let's just say you assume, you could still use this method, but what you would have to do is assume that it stopped and you would get a contradiction. And if you understood that it's a contradiction, you'd be great, but you also might be really confused and be like, what's going on? But here's what's going on. Say I assume V final is 0. That means this is 0. And that means PE final, which is negative GM over MM over R final, equals positive 2.75 times 10 to the 11. You would get a negative number for radius, which is impossible. You'd be like, wait, do I just ignore the negative sign? No, that's impossible. Sometimes we do ignore the negative sign if we're dealing with magnitude or something like that, and we can talk about that later, but in this case, it really matters. There is no such thing as positive potential energy for gravity. There are other potential energies in the universe, like electric potential energy can be positive. Any repulsive force, magnetic potential energy can be positive. Any positive force, any repulsion force has a positive potential energy, but gravity is always negative because it's always attractive. Gravity attractive, so it has a negative force and a negative potential energy always. Again, if you guys want to review that, I have the previous video on that. Come talk to me. I'd love to review why this is the case, but I am now using this fact to solve these questions. That this is negative, that if E total is positive and I'm removing all the kinetic energy, that's impossible. So it's impossible to have kinetic energy go to 0. Which means it doesn't stop. What does that mean? It doesn't stop. The rocket goes on forever. Isn't that cool? What I love about that, when I say isn't that cool, I mean, isn't that logic cool? Isn't it's the logical progression. We're not making any guesses here. Or if we make an assumption, what we're doing is we're proving something by contradiction. So if we assume it falls back and we get an impossibility, that's a contradiction, which means it didn't fall back, which means the rocket doesn't stop and it goes on forever. It escapes. It's impossible to have kinetic energy go to 0, which means it's impossible in this scenario. This is just one scenario. Remember, this isn't to be memorized as every time. This came from this information. This is fast enough. This is greater than the escape velocity. Turns out 20 kilometers per second, right, which was the initial speed, is greater than the escape speed. And we can derive this formula. We will do that next class. So it escapes. So what do we do? Well, instead of assuming V final went to zero, if it escapes, we now know that R final goes to infinity, which means, and I love that my little arrows means therefore or so. You can write this however you want. I do like little double arrow. Escapes. Therefore, right? You can do the therefore, right? Therefore. I like little arrows. Escapes. So therefore, our final goes to infinity. So potential energy final goes to zero. So it's actually the potential energy that goes to zero. It escaped. It came out of the well, right? We have a bigger force here. Force of gravity is the slope, a smaller force here. The gravity was not enough to slow the rocket down entirely. It slowed it a little bit, right? There was a little bit of work done by gravity, right? Force of gravity going in, velocity going out. The velocity here is smaller, here it's bigger, right? And here the gravity is smaller, right? It's a smaller slope. And here the velocity is a little smaller, but the gravity is so tiny that we have an excess velocity. And this is the potential. This is like graphing it in the potential energy space. This is the potential energy equals zero space. It has more than enough to go over the potential energy equals zero. I like imagining it as a well, right? In the actual physical space, it would look like this, where I have an initial V naught, which gets smaller and smaller and smaller, but again, asymptotically approaches some excess V final. Sorry, this should say V and not V naught. I apologize. Obviously, V naught is just at the beginning, right? Obviously. So it was some excess of V final here. And here's just V. V is just in between at some random point, V2 or V at point X or point R or time 5 or something like that. So here we have V naught, V1, V2, V3, whatever, all the way to V final, which is some excess. And we have a negative force, which is decreasing faster, right? The negative force is so tiny. The negative force is essentially zero here as it goes to infinity, such that the negative force is not enough to slow the rocket down. So this is the concept of, I say, what happens to F and V? This is the answer. Fg decreases, velocity decreases, but this decreases too fast. And this approaches some final velocity. The velocity that is like an excess. Right? The force decreases too fast. That's the answer to that question. So R final goes to zero, PE final goes to zero. That's what happens to that. So now we can say, okay, negative 2.75, sorry, positive 2.75 times 10 to the 11 joules, which is our E total, equals final potential energy plus final kinetic energy. The final potential energy goes to zero. And we could have assumed that, say you made a guess and you said, oh, it escapes. If you guessed that it escaped, you would get an answer for this, and that means you were right. It would be consistent. It wouldn't contradict. But again, you'd be missing the finer details in that guess. Of course, you could go back and fill them in. Totally. Again, if you want to do that, I love it. I love it in the sense that you're still going to get the picture, but it's a little more dangerous. There's a greater chance you might get lost if you assume this. But we now know this, we've proven it. And so we get that this is zero. So you get this equals 1/2 mv squared, 1/2 2,000 kilograms. Look back at your information. Always have it where your eyes look at m equals 2,000, right? Times v final squared. And of course, this is as it's approaching infinity. So this is a limit, right? It's approaching this number asymptotically. It's the excess. And we end up getting V final is, I just calculated it, 16,587 meters per second. right? Remembering that the initial was 20,000. So we decreased our speed a little bit, a little slower, but not much. We had a lot of excess, didn't we? So this is its escape speed. This is as it approaches infinity. It will approach this value. So it escaped pretty well, didn't it? And to me, that's pretty good. That's getting out there. Rewind the video if you wanted to go over any of those details. I hope that made sense. That to me is like the full encompassing concept, math theory of like the true formula of gravitational potential energy. See you guys in class. Ask questions, send me an email. I love it all. You guys are great. See you soon.